All right, let's start doing some calculations with acids and bases. One option would be a percent dissociation calculation. Sometimes they'll measure the strength of an acid by its percent dissociated. So here we have some lactic acid. It is a waste product, accumulates in your muscles. Excellent. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. Okay, so usually those are the two ways that we would measure the strength of an acid. Often it's by looking at the Ka value, how small or large is it. Or here, if it's only 3% dissociated, that's not by much. A strong acid would dissociate by 100%. So let's see if we can calculate the Ka. When we do these calculations, we're setting up ice tables. This is going to be great. Now you could start this ice table one of two ways. Obviously you have to have the reaction. Sometimes they'll write it like this. Here's the lactic acid, H5O3. And they'll show it just dissociating into maybe hydrogen and lactate ions. C3H5O3 minus. That is 1,000,000% just fine. It is totally acceptable to write your equation like that. Another option, which often for weak acids, they'll write the equations kind of like this. Lactic acid, H5O3. They might put water in there. And then instead of it being like free-floating hydrogen, they'll write the hydrogen as the hydronium ion, H3O+. And then again, we have the same lactate ion, C3H5O3 minus. And I will tell you that either way is 1,000,000% fine. Because here's what happens. As I set up my ice table, I'm going to go ICE. I start with my initial. I have 0.100 moles per liter of this aqueous solution. Initially, I have no products, so we'll put these in as zeros. And guess what? The water is a pure liquid on the reactant side, so we're not going to include the water anyways, which is why either way is fine. Like, if you saw it written like this, we can just kind of scratch the water, because we're not going to use the water when we finally set up our equilibrium expression. All right, so we have to shift this thing. We're shifting it forward. We are shifting it forward by this. It dissociates by 3.7%. So we're going to take our initial molarity and we're going to multiply that by 3.7%. So move the decimal spot 1, 2 by 0.037. And that's by how much I change. I mean, I could have to set this up as solving for x, but if they tell me the percent dissociation, that is x. That's by how far forward this progresses. So this guy's going to go down. It dissociates by 0.0037. So if I subtract, at equilibrium I'd have 0.0963. I don't care about the water. We're going to scratch that. And then these guys are going up by 0.0037. 0.0037. And these are like moles per liter. We could put that in if it bothers you. Up by 0.0037. 0.037 moles per liter. Fabulous. Now I got my equilibrium conditions and we can solve for K. Oh, that wasn't so bad. Ka equals products over reactants. So we will have 0.0037 to the first times 0.0037 to the first, and obviously you don't have to write a 1 in there. And then that's all over 0.0963 to the first. Not bad, huh? So we can plug this in our calculator. 0037 times 0.0037 divided by 0.0963. With sig figs, let's maybe leave about 3. How about 1.42 times 10 to the negative 4th? That's all there is to it. So this percent dissociation is like telling you X. It's the amount of the original that gets dissociated or the amount that moves forward to produce ions. The amount dissociated divided by the initial concentration. And again, that amount dissociated, that is like your X value. Another way of telling us by how far forward we should progress. Another option would be something like the second one, where now we want to calculate the percent dissociation for a 1 molar solution of acetic acid. Okay, so here's some good acid-base ice tables. This is why it was so good to kind of catch on to that ice table in the last chapter. You can apply it to so many different situations. Often they'll give you an equation. You're not usually coming up with this off the top of your head. They might list it like this. Here's the acetic acid, H3O2. Often for weak acids, they'll put water in the equation, and then they'll write this as H3O, and then the conjugate base would be the acetate ion, H3O2 minus. The acid is the hydrogen donor, water is the hydrogen acceptor. Alright, so we'll set up an ice table. ICE. We know the initial. It's 1 molar. We're going to scratch water the whole way through because it's a pure liquid, which is why, again, sometimes they won't put it in. And then on the product side, you would just see hydrogen ion plus acetate ion. Initially, these guys are zeros. So we know it has to shift forward. We have to have some product. But that K value is small, so whatever this X is, it's probably small as well. This is going down by X, up by X, and up by X. So at equilibrium, we'll have 1 minus X, X, and X. All right, so let's see what we got here. We'll set up our Ka expression. Ka equals 1.8 times 10 to the negative 5th. That should be on the top, X to the first, X to the first, whoop, all over 1 minus X. All right, so let's solve this a couple ways. Let's say that we are perfect rule followers. One option, you could cross multiply this thing. But eventually, we're going to have to use the quadratic, right? Because we're going to have x squared on the top, and then we'll have like 1.8 times 10 to the negative 5th minus 1.8 times 10 to the negative 5th x equals x squared. If that's your cup of tea, go crazy, and you can eventually solve this with the quadratic equation. That's to the first, not that it matters. However, when you're dealing with weak acids and weak bases, those K values are always small, which means the 5% rule is always a good option. It's going to save me from having to solve this quadratically. So let's try it. Okay, so let's get rid of this minus x. Because again, whatever x is, it's really small. We're going forward, but not by much. Man, does this make my math a lot more manageable? Because now I get something that looks like 1.8 times 10 to the negative 5th equals x squared. And I can just take the square root. And I would have, let's see, square root 0.00, how about 424 equals x? That's small, right? Do you feel like we should check the 5% rule? I suppose. Why not, right? Okay, so I made an assumption. I assumed that the acetic acid, H3O2, was just 1. When I did my calculation, I just used it as 1. But now when I calculated it, HC2H3O2, that acetic acid is really going to be 1 minus 0.00424, which is like about 0.1 0.996. Are you convinced that those differ by less than 5%? I certainly am. I mean, if I check it in my calculator, divided by 1. Yeah, it's like they differ by, oh man, this is ridiculous. Like 0.4%. I'm okay with that. So we could say here 5% rule checked. And to be honest with you, I probably wouldn't have checked that in my calculator. I would think about it. Like I just acknowledge x and make sure that x comes out to be something pretty small. So that if I were to go plug this in my equilibrium expression, oh yeah, like 1 minus x, that's pretty insignificant. Those numbers will differ by less than 5%. I don't always really calculate the percent difference. But I at least think about it, and I say that I did. We're going to say 5% rule checked. That's why we were able to simplify our math. Okay, so now what they really ask us for is the percent dissociation. The percent dissociation is just a measure of the amount that was dissociated divided by the original amount. The amount dissociated, that's x. So this is really like 0.00424. That's molarity, or moles per liter, divided by 1. Oh, that's nice. And then we'll move this over just a little bit. Then I can put my m in there for molarity. And then we should multiply by 100 to get a percent. Well, that's not so bad. Multiply by 100, this is going to end up being like 0.424% dissociated. There, that's my final answer. About 0.4% dissociated. That makes sense. This is a weak acid with a really small K value. Will it go forward? Sure, but not by a lot. The amount that was dissociated was only 0.00424 moles per liter. That amount dissociated, that is your x. By how far forward it goes, divided by the original amount. That makes sense for a weak acid or base, that the percent dissociation is really small.